All right. So let's just do a brief review of what did we derive last time. So this lecture is isothermal, so everything we do right now is isothermal, so we don't have gradients in temperature, because that would create a coupled situation. Isothermal equations of continuity and motion. What is the equation of continuity? By equation of continuity, physically. Mass balance. So balance mass. I'm trying not to lose mass. So that's one of the common ways to model almost everything. And these equations that result when we are conserving a quantity are called conservation laws, and are really the starting point of modeling of most phenomena. I'm conserving mass, I'm conserving energy, I'm conserving momentum, and that's basically when we have expressions for all the physical quantities, and I basically give myself a box in the coordinate system, and I balance what's coming in, what's coming out, or what's kind of changing through the boundaries in more general sense. Then I shrink that box to a point, and then I'll get a differential equation. That's essentially how we model most phenomena. So equation of continuity is a code name for mass balance. So what did we do? The basic idea is that if I have a fluid that is a non-reactive fluid, I have no reactions, chemical reactions that can result in something new forming the thing, and I look at the change of mass in a static box in a coordinate system, then basically what's changing that mass has to come out of those boundaries of the box. So any kind of volumetric change of mass in time, of course, if I have a flowing fluid within this volume element, that's going to be basically the net mass flow through the boundaries. Now, if I have fluid at the velocity v, basically the way I measure something bringing in, or what's traveling with that velocity is sort of like rho times v, so mass density times v. So basically, I look at rho v and project it on the boundaries. So if I do that, okay, if I look at this boundary over here, that is my boundary with the normal direction delta x pointing this way. So basically, to see something coming in through this box, I'm going to project that something that has velocity v, okay, onto this vector. And that's what's actually coming through this, because I have to go in normal direction to come through. So rho v dot delta x, right, projected on delta x, is what's coming in on this side. And that's my location x. I didn't denote it here, but this is location x. This is location x plus delta x. So this plane has constant x, and this plane has also constant x, which I refer to as x plus delta x. And on the other side, if I want to actually see what's coming in this direction, I project velocity in this direction, and I see what's coming in. Now, if I get something that is negative, then I know that it's actually going out. Okay? Technically, physically. But to actually see what's coming in, I'm going to project on minus delta x. Okay? And that way, for that coordinate direction, x coordinate direction, I have tallied up the contributions of what could have come in to my volume. Yes? And I just repeat the process for y and z. Now we have to write it down, and that's not necessarily easy, right? Everything that I said, waving my hands makes most sense. You know, I have boundaries to come in, I gotta go normal to them. So now we actually, so my projection is a dot product. So rho v dot delta x. So this is a coordinate vector in x direction. So that's actually my vx. in that coordinate system. That's how we actually think about coordinates in any coordinate system. They're projections on coordinate vectors. And then on x plus delta x, I have to do a dot with minus delta x. So basically, the net change in x direction is rho vx evaluated at x minus rho vx evaluated at x plus delta x. And this minus comes from the fact that if I'm projecting what's coming in, on the opposite side, I have to have negative delta x, or negative whatever it was on the other side. Okay. So when I also account, so physically, here's a box, right? And I'm going in. Now this is a fluid, it's not, it was just me going in, solid mechanics, right? I would just do my mass dot velocity in x direction, and I walked in. But that's not how fluids work. They have density that is distributed on this entire side, right? And when I walk in with velocity, right, I do a certain step in linear direction, certain width inwards. And if this was in my area, basically my change in volume is this area times that delta x, right? Walking in, or whatever was my velocity. My velocity was some delta in space. Right? So that delta space that is built into the velocity times the area will actually be the potential change of what walked in. That's the velocity interval of vx. So basically, what a measured change is measured by the area times v. Yes? Momentary volumetric change of the fluid. And when I multiply it by rho, I'm going to get the momentary mass change. Does that make sense? So that's why we have to multiply here with area. Because then I'm going to have volumetric change in time is my Vx times delta x times delta y. Times rho gives me the mass change. Is that clear? Should I go again? Good morning, it's Friday morning. End of the week. We're good? Okay. And the same on the other side. So that's why I'm multiplying by the area. Excellent. So this is basically my x direction, and I just do the same for my delta y. Delta y minus delta y, and top and down are delta z and minus delta z. So that gives me this rho vz and minus rho vz on the other end. So when I divide by my delta x, delta y, delta z, I will, on the left-hand side, get d rho dt. And these, actually, I can notice immediately my form of partial derivatives, which would, by the time you're ready for exam, you will learn to really quickly recognize, right? Because that's how we form the differential equation. So basically, this is going to be, as my delta x, delta y, delta z shrink to a 0, I will get negative dx of rho vx. Negative second line will be negative ddy of the rho dy, or rho y, and negative ddz of rho vz. And I then recognize the divergence. I recognize the divergence because somebody told me what divergence was, but really divergence as an operator was created to capture this. So we have a shorthand notation. A lot of different things, from mass to momentum to and so forth, we will get divergence term in there. If divergence physically is correctly stuffed through the boundaries, just think about it that way. And in that sense, it's related to a surface integration over a surface. All right. So basically, that is my equation of continuity. One thing that is interesting, if I put now rho as a constant, I have a constant density fluid, then this will be a 0. I can divide by rho, and I will get that for a constant density, divergence of V has to be equal to 0. And that's something that we commonly use in equations.
my velocity should be divergence free. So that means that locally I don't have sources and sinks. Because again, if I had divergence that is not zero, that means that I would have something kind of constantly reappearing at a point, or maybe leaving that point, right? So if I had basically negative divergence, this would be positive, and that means that my mass at a point or density is constantly growing, right? Without the element changing, and that means that I have production in a well, right? My divergence at that well point will be negative. If this was actually positive, then this is overall negative, so I'm losing mass. So I'm injecting something through that well, okay, in petroleum engineering. All right. And then one other thing is that components of viscous stress normal to the surface are zero. Now I'm making this normal to the surface. It's important to understand that if the surface is not aligned with the coordinate system, then I'm not thinking about those tau x, x, tau y, y, tau z, z, which are the normal components of the shear stress. They're kind of oriented normally to the surface. So that's just something to be careful with. All right. Same thing we will do if we do momentum balance, and that's something we've been actually doing with shell balances, because shell balances also imply steady state. It's not necessarily steady state. So we're just looking at things in time, and they might accumulate in time as necessary. So basically the change of momentum in time within the volume element is basically net momentum flux through the boundaries. And now the only thing is that my momentum is a vector quantity. It's not a scalar quantity the way density is. So basically, I'm going to have three equations as a result because I gotta go coordinate by coordinate. If I actually did the balance, and that's precisely what we do in shell balances, so I'm not going to repeat here. If I did the balance for all the x, the way I would, or for rather for phi x, which is the x momentum, the same way we did before, I would basically get the following equation. ddt of rho vx, which is my x momentum change. We used to have only rho here, right? Is ddx of phi x minus ddy of phi yx minus ddz of phi zx. And one thing I have to also recognize is that external forces can change momentum, so I have to add them here. And this is precisely what we would typically write. We would actually have it here as some version of this. In our thin film example, this part was 0, right? But other than that, I had everything else. Okay. So this is, by definition, this is a vector, really, that we refer to as x momentum. So it's x momentum going across x plane, x momentum going across y plane, and x momentum going across z plane. That's what I refer to as phi x, and this is really just divergence of that vector. And I have the same for y and z. And those are my momentum equations. And technically a shorthand notation for this, which is a lot to grasp, but it is helpful for writing things, is that d rho v dt is negative divergence of a tensor. So basically, divergence of a tensor has coordinates, these three scalars. Divergence of a vector is scalar. Divergence of a vector is scalar. So I have three scalars here. And those three scalars form a vector. That vector is divergence of a tensor. And formally, again, these things are defined essentially to make writing these three equations shorter. That's it. It's not there to torture you with vector calculus. Yes. So I got these three equations. We're okay with that? So each equation is basically momentum balance or in time, right? So this is conservation of x momentum, conservation of y momentum, conservation of z momentum. Now, phi x, you're okay with what this is, phi x? It's a vector with coordinates phi xx, phi yx, and phi zx, yes? This is my tensor. Here's where it's at, that vector. Yes? So this is my tensor notation for my combined momentum. Okay? Now, phi y, by definition, is three numbers that tell me how y momentum transfers across x, y, and plane, x, y, and z plane, yes? So phi y is phi yx, phi yy, and phi yz. Where can I recognize that? Phi yx, phi yy, phi yz. It's right here. So second column. Okay? And then this one is how my z momentum transfers across xyz plane. That's phi z by definition. And it's right here, zx, zy, zz. Good news is if you really flip these, it doesn't matter because these tensors are symmetric. So whether they're considered as columns or rows, it doesn't matter. So technically, I can then sorry, my touchpad is sensitive. So if I put this into a vector, these three numbers, they're essentially d rho dt of rho v. Are we comfortable with that? So the shorthand notation for these three numbers, when I put them in a vector, it's rho vx, rho vy, rho vz. That's rho v. Yes? Write it down on a piece of paper. Put rho vx, rho vy, rho vz into a column vector. So if I put rho vx, rho vy, rho vz, right, into a column vector, that's really rho v. Yes? Then this is d dt of rho v. So this is a vector. Has coordinates in the corresponding coordinate system, right? The first equation, or at least the left-hand side of it. Now, what I'm saying here, so this is my, let me change color slightly. So this is phi x, and this is phi y, and this is phi z. Yes? So up there, so I'm going to simply define divergence of a tensor is, so this is now tensor. Sorry, there was a line here missing. I sometimes drop those two underlined things that are just saying this is a tensor. So my divergence of a tensor is a vector where its x coordinate is divergence of the first column, its y coordinate is divergence of the second column, and its z coordinate is divergence of a z column, right? So just put together divergences of columns for a tensor. And if I had a larger tensor, I could do this
have to have just 3 coordinates, mathematically. So this is when the math steps in, and math says, well, it doesn't matter. You could have more than 3 dimensions. You could do this with 7 dimensions, should you wish, right? So the math normally defines divergence of a tensor mathematically is take every column, do a divergence of it the way you would treat vectors, and just put them all in a vector. That's divergence of a tensor. Yes? So this is just math stepping in to define something, to do a shorthand notation. And it's relatively easy to remember because we do look at tensors as a collection. My tensor is a collection of vectors, whether you want to look at them as row vectors or column vectors. Every tensor or matrix is a collection of vectors. Moving on. Yes? And again, divergence observation or something. Okay? I'm collecting or looking what's coming in and out of the boundaries, and that gives me divergence in the equation. That's just shorthand notation, but I do want to you probably in your math class, you're kind of just doing it mechanically. Here's what definitions are, here's how you calculate these things. Specifically for vector calculus, it came from dealing with electromagnetism and fluid mechanics. That notation was technically invented for that purpose, right? So it has a strong physical origin. And it can be applied to multiple things, not just electromagnetism or fluid mechanics. And I keep promising I'm going to put together a bit of a, maybe we do that on a Saturday or a Friday afternoon or something, but a bit of a short course on vector calculus through the eyes of transport or physical applications. I think that's technically sort of missing. But it's not going to happen before our exam, so maybe a bit after. It's still, I think, useful because it's very useful to conceptualize those things physically. As engineers, you're dealing with vector fields all the time. Machinery moves in coordinate systems, surfaces that are sitting in those coordinates, and divergence essentially collects stuff over those surfaces. So it's very important to consider. Okay. Yes? So yes, I'm torturing you a little bit with the vector calculus notation for the shorthand notation, but you should be exposed to it because it's pretty powerful. All right. So let's just compute now for practice. What is divergence of the tensor P delta? And by this I mean identity matrix. Identity matrix. So what would be divergence of delta? I have actually written this. This is a tensor. So I multiply my identity matrix with pressure. I get this, right? Divergence of a tensor, therefore the result is a vector. What is the first? This is the vector. Vector. What is x component of that vector? So it's going to have x component. It's divergence of this, right? It's going to be, whoops, big divergence of that.
divergence of any vector, I'm going to write it as a vector, let's say S, is dsx dx plus dsy dy plus dsz dz. That's by definition. If you forget that definition, there are those formulas. Anybody still needs a copy of this? But I have a couple of other copies. This is a copy shorthand from the book. Those are appendix. So the first table A71A will give you what divergence is. So what is, if I take this vector, I have 0, 0. So yes. Huh? What's the divergence of the second column? dy. What is this third column? The third column. dpdz. Oh, yeah, okay. So what is this? If you want tables, you will see that you got x, y, and z coordinates of the gradient. Gradient of v, yes?
Why do you not keep it in the 3x3 form?
Where? This is, I have zeros here.
Yeah.
This is a tensor. This is a tensor. That's my pressure component of the combined momentum. This is the number. There's pressure times the velocity matrix. Yes?
Yeah, so, well, for the,
Divergence?
yeah, why isn't it not just like filled with zeros?
So divergence of a tensor will be a vector.
Oh.
So this maps a tensor to a vector. Just like this, divergence of a vector is a scalar. And this is a number. So this is scalar. Scalar. This is vector. So divergence of a vector is a scalar. That basically integrates over this imaginary surface around the point that tells me if I have a non-zero divergence, I have sort of a source or a sink of that thing in there. Yes? And if it's zero, then I don't have any sources and sinks. But I gotta integrate over, and when I integrate vectors over surface, I'm gonna get scalar. But divergence, this is a vector, right? Vector. So divergence of a tensor is a vector. Yes? This is pressure gradient. Yeah? That's why I say that the flow is driven by pressure gradients. Especially one part of the, so this tensor is one part of the combined tensor field. Right? It's one of the driving things for the flow. Okay. Now, and again, the reason why we're into this is that my phi, what do I, here's what I have found about this design. There are two little things that should be in a different color and whatever, so I don't press them inadvertently, which I keep doing. So my phi is pressure component tensor, yes, plus convective component. So that is my combined momentum tensor, yes? So when I have, so this is a tensor and this is a tensor. So all of these are a tensor. So when I'm wondering, hey, what is divergence of this? I was actually just wondering what is the first component of this. Now, second part, whoa. Okay. I want to go further. There you go. Actually, let me give myself more space to write. Now, I also wonder what would be, so for Newtonian fluid, say we have Newtonian fluid. Can anybody tell me what shear stress is in that case? Newtonian fluid of constant density. Uh, 2 mu is what I typically get in the xx coordinate. Something's off with my. Okay. That one? And then that one transposed. And that one is called Jacobian. So it's a tensor that has all of the partial derivatives. That's fine. It's okay to call it that one. It's not going to get, it's a thing. It does not hold grudge. And as long as you can find that one in your notes somewhere, we're good. We're okay for exam. And then what else do I have? Okay. 2/3 mu minus some constant. And then divergence of V and identity tensor. So this is some constant. I have constant density fluid. What does my equation of continuity, aka mass balance, tell me about divergence of V?
should be 0. So that's a happy thing. Every time you have sort of incompressible fluid, constant density is incompressible. So basically this is gone. And that's great. I don't know what's up with my screen. It's not cooperating. 0. It says it's Friday. I've been deriving too many things. My screen is not happy. And neither are you. Okay. So this is basically minus mu. So here is an extra credit challenge. Okay. Derive for me for next time. What is this? This is divergence of this sensor minus mu divergence of the sensor. So basically, I want you to calculate this and that based on the definition of the divergence. What things is and what you should get that one of them is 0 and the other one is not. And what you should get as a result is a vector for minus mu, vector that has a Laplacian of Vx, Laplacian of Vy, and Laplacian of Vz. And is Laplacian. You can look at the Laplacian in this is table A71B. We will just use this result and define Navier-Stokes equation next time. But if you want the challenge that you understood what this calculus is, I'll do with that extra credit if you give me that derived. Just a fair warning. So next time, I didn't get to it today. Next time we're going to work through through a problem in class using a worksheet, and that worksheet will be then your quiz. So I have decided not to put this as a whole 5-minute thing at the beginning of the class. I think that's unnecessarily stressful. But what I'm paying attention to is during class and paying attention to. So if you work through the worksheet on Monday, does that make sense? So just as a motivation to work through and not sleep in class.